Hello and welcome to Mathematics with Simon. I'm Simon. Today we're going to look at Pascal's triangle as part of A-level mathematics. So this is Pascal's triangle. So it starts with a 1 at the top, then two ones, then there's a row that goes 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1 and so on. And the basic idea is that each element is the sum of the two elements above it. So 6 is the sum of 3 and 3. 4 is the sum of 1 and 3, 10 is the sum of 4 and 6, 20 is the sum of 10 and 10. And it keeps on going, so there's another row below that will go 1, 7, 21, 35, 35, 21, 7, 1. We notice that it's symmetric around this central line. It's perfectly symmetric. And so we look at Pascal's triangle, and then we look at something else, which is all the powers of x plus 1. So here's 1, x plus 1, then x plus 1 squared is x squared plus 2x plus 1. X plus 1 cubed is x cubed plus 3x squared plus 3x plus 1, and so on. And if we just flick between them, that's the powers of x plus 1. That's Pascal's triangle. That's the powers of x plus 1. That's Pascal's triangle. That's the powers of x plus 1. We notice that it's the same numbers. So if we just take a row, 1, 5, 10, 10, 5, 1, for instance there, 1, 5, 10, 10, 5, 1. Then here, 1, 5, 10, 10, 5, 1. Next down, 1, 6, 15, 20, 15. 1, 6, 15, 20, 15. And the question is, why? Why is this happening? What's going on? Isn't it fascinating? And the answer is another way to write Pascal's triangle. So this thing, another way to write it is this, which is, in the last video we looked at combinations. So this, for instance, is how many ways can you choose 1 from 2 with the order not being important. And this is how many ways can you choose 2 from 3 with the order not being important, or 2 from 4, or so on. So this is actually another way of thinking about Pascal's triangle, and if we just do the numbers, we'll find that it's the same as this. So let's flick between them. Let's put them together. We're going to flick between them. So just for example, this is choosing 2 from 5, which is 10. This is choosing 2 from 6, which is 15. This is choosing 3 from 6, which is 6 factorial, 5 factorial, 4 factorial, divided by 3 factorial, which is 20. So basically, this is what's really going on in Pascal's triangle. It's sort of all the different ways of saying choosing R from N. And so R counts across, let's take the bottom row, R counts across 0, 1, 2, 3, 4, 5, 6, and then N is the row. So the rows go 0, 1, 2, 3, 4, 5, 6. So in other words, how many ways are there to choose 0 from 0? Just 1. How many ways are there to choose 0 from 1? Just 1, or 1 from 1? Just 1. But basically, it's NCR, and N is the row, and R is like how far right you are. So R starts at 0 on the left, and then R goes to N on the right. So the question is, what on earth's going on? Why is this happening? And if we just pick somewhere in the middle of Pascal's triangle, what needs to be happening, what must be happening, is that if we choose R plus 1 from N plus 1, we know that that is the sum of the two above. So the two above will be R from N and R plus 1 from N. That's kind of what must be happening to make all of this work. So we've got to prove that choosing R from N and choosing R plus 1 from N, if we add those two numbers together, we get the same as choosing R plus 1 from N plus 1. So to check this, we're going to expand out the right hand side first. So we know the right hand side is N plus 1 factorial over R plus 1 factorial, and then you've got to take R plus 1 from N plus 1, which is just N minus R factorial. This NCR is just n factorial over r factorial n minus r factorial, and this NCR plus 1 is n factorial over r plus 1 factorial n minus r minus 1 factorial. And then what we're going to do is put these things over a common denominator. I mean, are these a bit small? Should we make them bigger? I don't know. I mean, we just make them a little bit bigger. Is it going to work? There'll probably be a wrapping problem. No, there's no wrapping problem. It just looks a bit nicer, doesn't it? So what we're going to do is put them over a common denominator. And the common denominator is the one we've got on the right, which is r plus 1 factorial n minus r factorial. So here, to get this thing into the common denominator, we've got to multiply top and bottom by r plus 1. So we get n factorial times r plus 1 over r plus 1 factorial n minus r factorial. And then to get this to the common denominator, we've got to multiply top and bottom by n minus r, because n minus r minus 1 factorial times n minus r is n minus r factorial. So what we get up here then is n factorial times n minus r. Here we get n factorial times r plus 1. And then if we add those, they're now over a common denominator. As if by magic, we get n factorial times n minus r plus 1, which cancels to n plus 1. So n factorial times n plus 1 is n plus 1 factorial, and we've proved the identity. So this is why it's all working. And then what we also need to remember is this, is that if we expand out any power of x plus 1, we've just taken the fourth power here, the fourth power of x plus 1, what that comes to is 4c4 times x to the 4, 4c3 times x to the 3, 4c2 times x to the 2, 4c1 times x plus 4c0. And the reason is because if we're looking for x to the 4, we've got to choose all four brackets, because we need to choose x in all four brackets. We need to choose x in all four brackets to give us x to the 4. If we're choosing x cubed, we need 3 brackets with x in, and then the other one's just going to have a 1. So we're choosing 3 from 4 to have the x in. So there are 4c3 ways of getting x cubed. There's like, we take the first, second and third, the first, second and fourth, the first, third and fourth, and the second, third and fourth. Altogether that's 4 different ways. If we want to get, if we want to make x squared here, we choose 2 of the 4, where we're going to multiply in the x. So in that case, the coefficient of x squared is 4c2, which is 6. So the point is, these combinatorial coefficients are what you get when you expand out x plus 1 to the 4 or to the n more generally. So if it was x plus 1 to the n, you'd get ncn, ncn minus 1, ncn minus 2, going down right at the end to nc0, and this one would be nc1. So that's how this whole thing fits together, and that's why Pascal's triangle is relevant to the expansion of x plus 1 to the n, because in a sense Pascal's triangle gives you the combinatorial coefficients, and then the combinatorial coefficients come in here when you expand out x plus 1 to the n. Also, by the way, this gives us a proof that NCR, which is n factorial over r factorial n minus r factorial, is always an integer, is always a whole number, because it's not obvious from this that it would always be a whole number, but the way we know it's always going to be a whole number is this. We know that in Pascal's triangle, we start with 1 and then 1, 1, and then every row below, each number is the sum of the 2 above it, and the sum of 2 integers is always an integer. So we start off with integers, and then we make more entries which are sums, either just a 1 if it's on the left or the right, or a sum of the 2 above. And when you add 2 whole numbers, you always get a whole number. So this gives us an automatic proof that that this coefficient is always an integer. Further math students will recognise that this is a proof by induction, and it's induction on the row, or on the position of the coefficient. But essentially, it's just kind of obvious that if you're adding together integers, you get integers. Thank you. I hope you like this video. Please subscribe and hit the notification bell if you want to see more videos. I'd love to hear your ideas, and most of all, I hope you enjoy your mathematics.